Okay, this is review session number 12, all about sound and light and how they're different, how they behave differently, and then the next one we'll get more into the specifics of light. So one of the things that, sound and light can both do is something called diffraction. Okay. And diffraction is basically when a wave bends as it goes through some sort of opening. So if you have two barriers, and you have a series of waves coming through that barrier, they're heading in this direction. As they go through that barrier, they curve. The friction between the barrier and the medium itself starts to curve that wave, and so that's called diffraction. Now, things that affect the amount of diffraction, how much it's curved, is the distance right here between these two opening, or distance between the two barriers, the opening size. If the opening size goes down, the amount of diffraction or bending goes up. Okay? The other thing is the wavelength of the wave. As the wavelength goes up, it's going to bend more. So the diffraction itself goes up. So that's one called a one-slit diffraction. You can also have the double slit where you have two openings as they go through, and you have your wave as it travels towards it, and then you're going to start to get the same phenomenon occurring. Wow, it's a horrible drawing. Okay, but then you also have it from both parts. So when you do it through two of them, parts where these waves overlap, like you see here and here and here, you're going to get interference, either destructive or constructive. If it's a point where you have two troughs meeting, it's going to be constructive interference. A crest and a trough meeting, that's going to be destructive interference. Now, another phenomenon that occurs with light and sound is called the Doppler effect. And in class, we went through a whole series of equations where we can calculate different aspects of the Doppler effect. You don't need to know those equations, okay? Basically, what you need to know is that the Doppler effect is the apparent. It's not an actual change. It's just the apparent change in frequency or wavelength of sound or light from a moving source or a moving observer. So if it could be something like, a car approaching you as you stand on the side of the road, okay? Or it could be a car standing still and you're approaching the car, right? So in this first case, we have the moving source and a stationary observer. In this case, we have a stationary source, which is the car, and a moving observer, which would be you. Now, excuse me, if the source or the observer are approaching, therefore, we're going to have a perceived increase in frequency, decrease in wavelength, because remember those two are opposite to each other, they're inverse. If the source or the observer are moving away, then we're going to have an apparent decrease in frequency and an increase in wavelength. That's what you need to know. And it can be light as well. So as things, move away from Earth, as a distant galaxy moves away from Earth, its light is changing. The frequency of the light that we're perceiving is changing, as opposed to a galaxy that might be moving towards us. It's called the red shift and the blue shift. Now, like we've said before, sound is longitudinal. And it needs a medium. Because it needs a medium, it cannot travel in a vacuum. A good example of a vacuum, space. Okay? So sound cannot travel in space. Light can. Light does not need a medium. Okay, all electromagnetic waves, they do not need a medium. They can travel in space, which is why we get light and microwaves and X-rays and radiation from space, because they don't need a medium. Okay, we do not get sound from space. Otherwise, all we'd hear would be constant nuclear explosions from the sun. So those electromagnetic or light waves, just remember that it's not just light. Okay, it can also be things like FM radio waves, AM radio waves, X-rays, ultraviolet, infrared. Those are all part of what we call the electromagnetic spectrum. They're created when a charged particle is accelerated. Okay? When you accelerate a charged particle, that creates an electric field. Okay? If you create an electric field, you then have a magnetic field, which is a capital B. So you're generating, and that magnetic field in turn generates an electric field. That electric field in turn generates another magnetic field. So that's how these EM waves travel. And these are transverse waves. All right. Now these EM waves travel at 3 times 10 to the 8th meters per second. Okay, this is for electromagnetic waves or light. Okay, and that's in a vacuum. Okay, that's also known as C from Einstein's equation, E equals mc squared. Sound has a velocity of 3.31 times 10 to the second, or 331 meters per second. That's at STP, standard temperature and pressure, that's 0 degrees Celsius. But for sake of equations, that's what we're using for the regions, unless otherwise stated. Okay. Now, as you can see, light, I don't know why my little stylus is not working today. Light is approximately 1 million times faster than sound. Wow, the stylus is horrible. Okay, so that's why you typically see things, well, not typically, you see things before you hear them. Okay, lightning and thunder happen at the exact same time, but you see the lightning before you hear the thunder. Now, a couple other differences. In terms of EM waves, what makes something a gamma ray as opposed to the color red is simply a difference in frequency and wavelength. Okay? And on that chart in your reference tables, it shows you the frequencies, relative frequencies and wavelengths of those different light rays. So it's really just a difference in frequency and wavelength that, you know, is a difference between tuning your radio into something and seeing the color blue. It's just the frequency of the source that's emitting that light. And another thing, last thing that we'll talk about here, is how density affects sound and light. Now, in sound, okay, if the density of the medium goes up, then the speed goes up. Because sound is, like I said, a longitudinal wave, so the molecules have to bump into each other. So if it's more dense, the molecules are closer together, and therefore you're going to have faster speed of sound. In light, since light doesn't need a medium, you can think about density as just getting in the way. So if something is more optically dense, so it still allows light to travel through it, but it is more of a dense medium, still transparent but just dense, the speed of light, the velocity of the light goes down, okay? Because that medium kind of gets in the way of the light. Now the next videos will be on refraction and reflection, and those get their own separate videos because they're a little more in depth. So if you have any questions about sound versus light, just ask.